Cook, and today we're going to be talking about photonic crystal surface emitting lasers as part of my informative speech for Communications 1010. So I did this research over the summer at the University of Michigan. I was at the University of Michigan on what's called a REU, which is a research experience for undergraduates. And what that is basically you go to a different institution and conduct research for 10 weeks during the summer. And this research I did with part of the CFOAM group, which is a division of electrical engineering. So CFOAM stands for the Center for Photonic and Nanoscale Materials. And so what we did is with the nanoscale materials group, we fabricated surface emitting lasers. So I worked with the group of Dr. P.C. Koo at the University of Michigan, and he is a professor in electrical engineering. And his group focuses on energy-efficient optoelectronics. And what that means is they engineer materials to achieve higher efficiency through interactions of light and matter and electronics. So his group focuses mainly on making materials out of gallium nitride, which is a semiconductor. So his group patterns things out of semiconductors, such as LEDs, quantum dots, and they also grow semiconductors atom by atom using a process known as epitaxial deposition. And the two grad students that I worked with over the summer were named Chusheng Tang and Brandon DeMoria. So a little bit of background before we get into the surface emitting lasers. We need to talk about a little bit of solid state physics. So if you think about a crystal lattice, the crystal lattice, all the atoms are arranged periodic in all three spatial dimensions. And the spacing between all these atoms is what dictates what wavelengths or energies of electrons will pass through this crystal and flow. And the energies here are given as in quantum mechanics, like the de Broglie wavelength as we have here. And this diagram here actually shows us what's called a band gap diagram. So what it is it shows us the energy between the lowest point of the conduction band and the highest point of the valence band. And this energy is what dictates which energies of electrons will flow through our crystal. So now we're going to get into photonics. So what photonics are is it's the interaction between light and matter. And so on the nanoscale, things behave according to quantum mechanics versus classical mechanics. So on the quantum mechanical level, atoms and electrons and everything behave differently. They behave as waves rather than point particles. And you can actually use this to your advantage to fabricate more efficient nanostructures. So what Dr. P.C. Koo's group does is they manipulate the light as you would electrons in a crystal lattice. And when you do this, you can achieve things like signal processing, arbitrary directional transmission of your light beam. You can use it to build extremely sensitive biological and chemical sensors. And you can actually engineer photon-photon interactions, which, according to classical mechanics, photons don't interact. So the fact that you can increase the interaction between photons is a very good aspect of photonics. So photonic crystals are what we actually studied over the summer. So what a photonic crystal is it's an artificial periodic nanostructure engineered out of a semiconductor. And that sounds really complicated, but all it is you have to think about we're basically patterning the semiconductor analogous to how electrons are arranged, or atoms are arranged in a crystal lattice. So depending on whether you make a 1, 2, or 3-dimensional photonic crystal, your structure is going to be periodic in that many dimensions. And photonic crystals are nice because analogous to the electrons in solid-state physics, based on what material you engineer, different wavelengths of light are going to propagate and behave differently in that structure. And these two figures here, we have what are called natural photonic crystals, or basically just photonic crystals that occur naturally. And so here we have different species of insects like butterflies and beetles, and then on the right is an opal, which is the most well-known photonic crystal. So photonic crystals you can use, or you can engineer to make things like waveguides. You can make nanopillars. You can make Hall arrays, and you can make inverse atom structures. So basically what you do is you create a structure that's analogous to a crystal lattice, and then you etch it out so you have the inverse of it. And all these things achieve different goals depending on what kind of photonic crystal you want to make and what your end structure is going to be. So this is what I actually studied over the summer, which is a photonic crystal surface emitting laser. And what this is, it's a photonic crystal that we engineer and encapsulate in a structure such that when we eject energy into it, light is emitted vertically from the crystal, and it's actually laser light, which means that it's coherent and in phase. And so what a photonic crystal surface emitting laser is, it's a nanoscale laser etched from a single piece of semiconductor crystal. And the laser actually consists of several parts. You have the photonic crystal, you have the cladding on the top and bottom to protect it from the environment, you have means of injecting energy into the system, and then you have an active layer to supply the electrons. And the electrons are what's known as quantized or confined, so that the energy emitted is also quantized or emitted in discrete wavelengths. And then here we actually see the whole structure of the photonic crystal surface emitting laser. So as I said, we have our actual photonic crystal here in this region, and then on top and bottom is the cladding layer, which protects the crystal from the environment. Inside the photonic crystal, we have our active region to supply the electrons, and then on top we have a structure that's fabricated so as to collimate the beam when it exits the crystal. And then on the right here, we can see the actual holes that are etched into the photonic crystal to achieve our periodic structure. And the top is a top view, and then the bottom is a side view of the crystal. And then here is a crystal that our group actually made. So this is a photonic crystal surface emitting laser. The whole package is built, and here we can see that it's lasing at the blue wavelength region. The left photo is an actual photonic crystal surface emitting laser, and then the right photo is the far field pattern of the laser looking down from on top, from far away. And these lasers are nice because they operate at room temperature, they have very low beam divergence, and you can actually produce high power, very circular beams with very low input energy. So they're very efficient. And these are awesome because people are thinking about integrating these into computer chips so that you can do logic with light instead of electrons. And that was my research for over the summer. And I got some references for this presentation.